So back again from the break. Let's see, I got unmuted, good. I don't know what happened. Probably I lost a loading of an image at some point. Anyway, now I have produced an image where we see the skeleton. And now each segment is marked up with the width. And width is based on a distance map. And then they're color-coded according to the maximum width in that segment. We can look at the histogram and see that the main width in this histogram is about 5 pixels. And that is where we have the most representation. And then we have some that are longer and some that are less. Natural choice would be to prune out everything that is at least less than 4, possibly even 4, I don't know. That would be, have to check what it looks like. Maybe we start losing real segments if we take away the 4. So now let's look at what this skeleton would look like when we do pruning to the 4.5 actually. And then it's pretty nice reduced. You can also see how well it fits now to the ground truth. Just as a comparison, where we started, this was the medial axis skeleton. And it's much more complex and it contains a lot more information than we wanted. So in this case, it looks like a combination of thinning and pruning based on the segment width. We get a nice skeleton that represents the street in this picture. Now we want to look at more information. We can use same criteria now to look at the image that we did before. Now we just run the convolution again on the image and see what comes out. We can find segments, junctions, and endpoints. And the analysis now, we can label different points. So we have different endpoints. As you can see, some of them maybe not really end up where we would like them to. And this one end up behind the bush or the tree. Then we can see that there are, of course, junction points. Some are real, some are not. But that is also an effect now of the missing, of the wrong, of the still remaining branches that shouldn't be there. But anyway, we get a nice analysis of this street now. Next thing we want to look at is the topology. How are different regions connected? And as a starting point, I want to have a very simple image. This one is a 3 by 4. We have node, and edge. And after labeling these, we get first label node labels 1 and 2, and edge labels 1 and 2. And now from that, we want to see how they overlap. And for that, we use the dilation of the nodes and to see which edges actually overlap with these nodes. So it's more or less just you have the node, and then you see with the dilation, you can see how it fills over. And then on the next slide, let's see if we can go down. Yep. So here we have the nodes, got them labeled, and by dilating node 1, we can see that it becomes a blob like this, and this blob actually overlaps with edge number 1. If we do the same again on node number 2, we can see that it gets a blob, and this blob overlaps edge 1 and 2, and then we can see that we found 2 edges in this neighborhood. This is a very small example, but it's always, it's the same actually if you do it on a larger context. You just have to count more. So let's take a look at what happens. Here's the code for doing this kind of analysis, and we can see that edge 1 connects to these nodes, edge 2 connects to these nodes, and so on. It's a long list because we have many nodes. And then we can get this map here. Can even color code it or put alpha coding on it to tell a little bit more about it. An interesting thing is to compute the connectivity matrix to see how many, how long segments are connected with each other. So what you have here is node A and node B, no, node A and B, sorry. And you can see here that node A is connecting, no, node B number 3, I think, is connecting to pretty many nodes in A, 3 nodes. And then I would guess it's probably one up here or something, or because it's a pretty complex one. And these are connecting with very long nodes. So that gives us the yellow color. So I would guess it's around here in this area. And so on. So this matrix, the more connected this skeleton is, the more you fill out the connection matrix. A metric that is interesting in many cases is the tortuosity, and that is the, well, actually there are many metrics on it, but a simple one is computing the length of a segment and divide it by the distance between the start and end points, so Euclidean distance between them. And that gives us a number that tells a little bit about how much meandering this segment is doing. That is useful for many applications in geology, in porous media research. When you want to look at porous systems, you want to see how much, how often these segments are changing direction, and that has then an impact on, for example, the fluid dynamics in the system. Also, vascular tissue can be used as a sign of pathology in the medical application. So it is a good number to take a look at least to measure and see if it correlates with some other information that you are interested in. So now looking at these structures, the tortuosity was computed for all the segments. You can see most of them, they are around, so say 70, 80, 90 or something. And then there are some exceptions going down to smaller values like this one and this one. It's probably small segments, so they can't twist so much. And now we can also make a little graph, a different way of visualizing the whole network. This is a randomized graph, so it's just putting to show the topology, not the geometric positions, but more how much it's branching, and to get an idea how much the network is branching. We can also color code it in this picture again. Now it's color coded by I think it's the tortuosity. To check again. Where is the alpha? It's always the same. It must be that one. I don't find it. That's also typical. That's about the width of the street. So you can tell here about how wide the segmentation is. So apparently these parts are wider than these, and so on. So you can do a lot of color coding, makes it possible to do, again, a visual feedback when you're doing the analysis And also it's easier to discuss around something when you have this visual feedback. Then we can also look at the graph to see how much it connects. Again, sorting out, sorry here, I didn't, so here is how many nodes, or how many edges each node is connecting to. So apparently in the street, most nodes are connecting to two elements, to two edges, and then there are some few cases when you have 4 and more connections in this street. So it would be here. Let's see. Let's plot X label. Oops. Number of connected edges, and we have the Y label. Nay. And that one is number of, oops, nodes. So now it's annotated in the way it should, almost. So this is also an analysis we can do about this graph. And now we can take this, so 2D is one thing, but in 3D, you can do the same skeletonization, more complex algorithms. You can also have more complex neighborhoods to analyze. I think if you want to read more about algorithms and how to compute skeletons, there was a survey made by my colleagues in Uppsala in Sweden, a group that had been occupied with skeletonization algorithms since long time, I don't know, 20, 30 years. So they have a long tradition in developing these skeleton algorithms. Let's look at an application of a 3D skeleton. So I have a root network, which was provided to me by my student, Guido Parenza. That was segmented using a UNet deep learning algorithm to find these root networks. So why do we want to look at root networks? One thing is soil stability. Another one is water uptake or distribution within the root network. And also, how is the root growing under different conditions? So what we want to know is to look at the network morphology and things like segment length between branchings, how much it branches, and also what is the orientation of the different branches. Another further thing is to look at influence volumes. So if you have the skeleton, looking at which volume does this segment take into account when it gets water and nutrition. So these are things that are questions that are coming up with root network. And now I loaded a root image, the segmented one, and looking at the single slices, as you can see, it's hard to see in 2D with a thin structure like this. So instead, I did a projection in one direction, and then you can see what the root network looks like. Still, it's not skeletonized yet, so let's do that. I ran this, it took a little while, so I ran it in advance. If you want to play with it, and actually you will play with it in the exercises, the data is already uploaded on GitHub. It was so big, so I needed to compress it, so you have to uncompress the data when you start doing the exercise. But this is what the skeleton looks like in the projection with the screen resolution I have right now. But if we look at it in a more detailed view, we have the segmented root here, and then we have all the skeleton, and you can see that there are some regions here which are not connected, and these you will identify during the exercise when you do that. So now we leave the skeletons and go into touching items, and that's a problem, as you could see before in the connected component labeling, and it's actually used a lot. It's an algorithm that's used since, actually, I don't know how old it is, but I think it was developed during the 90s, and it's still used also in machine learning applications. So for example, here was some kind of Kaggle competition, and the guy did a lot of fancy stuff with his deep learning, and then in the end he added on a little bit of Watershed segmentation and morphology for post-processing. Like, that was his recipe. So Watershed is coming up all the time. And image processing, in particular when you want to identify individual items. So what we have is are these data. We have the cells, we have it as grayscale. Then we do some segmentation and get these labeled items. And you can see, if we do just a simple component labeling, there will be some touching objects. And we don't want them like this. And this is what's actually already preloaded. So it was someone else who did it. But we are going now into trying to segment these images. But you can also see that there is a difference between the auto segmentation and this clean image. So they have done something more to the data than we did, just doing the plain auto segmentation. So let's try it. Here we have now a really heavy close-up of this cell data, where we have the grayscale. We do the segmentation. You can see that it's nice black and white. And do the connected component labeling, we get 2 items. When we look at the ground truth, we see that we actually 4 items should be present in this image. So we did something wrong. So now we need to see how we can improve this. So the watershed segmentation is the solution, and sounds wet. And actually, the reason for the name is that there's an analog to landscape. If you put a droplet of water on somewhere on a mountain, it will in the end flow down to the bottom of the valley, where usually there is a lake or a river. So that is actually the principle of the watershed algorithm. And if you have a black and white image, you don't have this landscape. So what we need to do then is to create it, and the distance map is actually providing it to us. So let's take a look at a distance map of this sample. So here you can see we have some snow-covered mountains, and we have the valleys. And now if we put water in this, you will see that the water will flow either in this direction, in that direction, or in that direction. And now what the watershed is doing, it's actually filling up more and more water until the water from 2 valleys are touching each other. And the algorithm is then building a dam between here and filling it up. And then you continue filling water until you only have filled regions and dam pixels between them. And the same, the water is coming here, is also filling up. And in the end, what we will get from this watershed segmentation is at least a little bit better segmented image. So going back to this, we can see we have our black and white. We compute the distance map. We can see clearly we have a top here, we have a top here, we have a top here. And here we have a saddle point. And apparently this peak local max algorithm identify this also as a local maximum. Saddle is actually not a local maximum in the sense that we want, but let's see what happens now. So now when we run the watershed segmentation on this, you can see that the growing is producing one segment here, which was what we wanted. Also one here, but it produces one in here as well. And that is not really what we wanted. The ground truth actually produced something up here in this corner, and we didn't do it. But the reason we didn't do it was that Otso didn't find it. So if the black and white doesn't find it, then also the watershed can't find it. So for that, we leave that piece in the corner here for the moment. But what we now want to do is to get rid of this annoying thing in the middle. And by doing that, we start removing small elements. So we start measuring the area of the labeled elements and see that we have 3 which are pretty big and 1 is definitely very small. So that's not really a relevant one. And now if we take that one out, we can start having these seed points again. And then you can actually produce nice 3 segments of the main blobs here. And again, we lost this one, but that is to be expected. I think, I don't know if it was last week or week before, I got the question if we can decide what the label is on the elements. And with this approach here, we can actually give whatever labels we want. If we start with renaming these seed points, then also the labels of the regions, they will get that label number. So this is a way to produce these, to make a choice on how they are labeled. And now we have to scale back up. This was a really very close up. So now let's look at the whole image. And when we do this, we identify a lot of items. We run the watershed on it, and yay, we got a lot of segments, but somehow we got, in some cases, we missed some. That is probably because of Otso didn't find them. But in other cases, like this item here, it was split up in several items, and also this one, and it doesn't look like at all like the ground truth. So we got not the performance we wanted, and that one didn't execute. Okay, let's go back again. So let's execute this one. Takes a little while. Oh no. Okay, so that wasn't meant to be. I go to the next slide. So anyway, I was just about to show the same panels I had before. But in principle, what we have over-segmented cells and we have missing cells. So we need to do something about that. And one reason for the bad performance is we used Otso. We need something else, as we already have seen. And also that these cells, they are not perfectly smooth on the surface, and that produces a lot of local maxima in the elevation map. So the solution to get around with this is, first of all, use a better segmentation. The histogram seems not to be the right choice. And also to use different morphological algorithms, like there is one called maximum impose. And that's described in the book by Soil. Actually, a really good book. If you want to look into morphological image processing, this is the book to go to. It's really good. One thing is he makes a good review of all the different algorithms. and the methods you can use. And also, he produces pseudocode, which is very good written. So it's actually possible to implement your own algorithms from his pseudocode. Sometimes it's so well written that I actually compiled. I wrote my C code and compiled it, and it actually worked on the first time. Nothing that I usually don't expect. So that was really a good piece of pseudocode. Now we switch to another example, and this is from a battery. So we're looking at the anode of the battery, and the background information for this you find in these two papers, and mainly in the first one, but the second one is also going in the same direction. The difference between them is in the first one, the items in the image that we can see, they are round or almost spherical, while the other one is more irregular structures. So it's a little bit different in shape. What we want to segment and quantify the relevant structures. So we want to know how large they are, what surface area they have, possibly also what they how regular they are. So if they are spherical or oblatoids or something like that. And that is more about the geometry. But the interesting thing is to look at what happens within the battery at different pressures and compare what the sample look like if we have added some pressure to the sample. And what it looks like is something like this. So it looks like just a ball packing of some kind with some grains in it. Some of these grains, they look like they have cracks inside. And then we apply auto segmentation, which produce, I would say, on first sight, a pretty good result. Then we can clean them, get rid of a little bit of misclassifications by applying a closing. And now we let the water flow, so applying the watershed segmentation and following the steps, producing a distance map, getting the watershed labels. Right now I used a color code which is continuous, so you can see that we have the smallest labels up here and the largest labels here. It doesn't give you any information, as the label is just an index number, so it doesn't tell much about the sample itself. It's just how many we have found. Looking at the watershed boundaries, it looks like sometimes we do a good job, and other cases it looks really crazy, like this one. And that is the well-known over-segmentation caused by the watershed segmentation. And to get a little bit more detail, there was a little bit too much, so we crop it and look at a tinier area. So we have the image here, the distance map that it produced. You can see that there are some interesting places around here, the rings, the crests, and so on. And if we continue looking on the continuous color map, you barely see anything. You can see that it's gradually increasing here, but looking a little bit closer on, for example, this one, you can see that it is actually 3 different segments. So now we come into the choice of color map. So I changed to a one called flag, and then all of a sudden you can see that it's a pretty crazy thing that we have segmented here. And that is, actually, I think something went wrong here. I have to go back. So this is what I wanted to show. I somehow got the inverse. I don't know why, but that is what I got. And let's go back. And now you can see really nice that this circle is segmented in, I don't know how many segments. Also the crest here is also divided into pretty many. So essentially each item is over segmented, and that can be a little bit annoying. So again, a good idea would be here to impose some good minima and merge all these over segmented items. Another way would be to look at, still use this, keep it as it is, and represent it with a graph. And now comes a pretty big piece of code, but in the end, we come up with a graph where we see that we have connected items and see which ones are actually getting closer to each other. You can see that there are some pieces that are islands, like this one, these ones out here. You can see that some are touching, and you can see that some are touching in a really complex network. So this is a way to start looking at how well connected is this anode. And in an anode, you want good electrical conductivity. So you want in principle, you want all items to be well connected. Now, let's continue on this and look how different are connected. We get this data frame where we see a little bit more about how they are connected, how long the interface lengths are, the distance between the nodes, width of the items, etc. And now we want to see what happens, and we need a little bit more data again. And then in the end, we have this graph again. I need to get, here we get the connected graph. Now we can see a little bit more how some are more connected than others. So for example, in these crazy areas, there is a lot happening. In other cases, we only have one or two connected regions. And this graph, if all were connected to all, that would be filled within here. And then here you can see now some are connected along this border here. It's a way to show it. Interpreting it is another question, and that comes probably from the electrochemistry, which is not really my thing. So I can't really put the value, any value on how this graph is, why this graph is connected like this. Another one is to look at the histogram and of how many nodes are connected with each other. So we see that we have many disconnected nodes, so that is a 0. Then we have a couple that are connected pairwise, and then very many are connected with 2 neighbors, and that are those that are connecting and providing a nice network. And then, of course, we have the more branchings here, and in the end, we have crazy regions with up to 8 connectors. So going back on this slide again, looking at this is a single 2D image sliced out of a 3-dimensional object, and it's only used now to visualize how you can use watershed segmentation in 2D. But the real sample is actually 3-dimensional, and when you start doing the watershed segmentation and graph analysis of the 3-dimensional, I would expect that we have a much greater connectivity than the histogram shows on the other slide. So all these items are probably connecting with each other, even though they're not showing it in this particular image. So that also gives the message that if you have 3-dimensional information, use it, because you will otherwise lose relevant connections that that are really necessary to make the conclusions about the data you have. And the good thing is the watershed segmentation is easily expanded into any dimension, actually. So it's the implementation is just about looking in a little bit greater neighborhood, and then you have the same procedure in 2D as in 3D. So that is it's really important to work with the three-dimensional data if you have it. And that brings us to the end of today's lecture. So I have been talking about skeletons, mostly in 2D, but also in 3D. One little comment here that I forgot to say, that the skeleton in 2D is reducing by 1 dimension. So we get lines between nodes. In 3D, you could actually also reduce to not only to lines, but also to planes. And some algorithms, they actually not only produces the lines between the nodes, but can also produce some kind of planes that are describing the topology. For some applications, it can be useful. In other cases, you want to get rid of these planes and reduce them into single lines as well. So again, the choice of algorithm depends on the application, and you have to be know what you want before you start selecting the algorithm. Watershed is a great algorithm. It's used very much in many applications. It is able to label touching items. The case when connected component labeling doesn't make it. I write here, it may oversegment. I would say, in principle, it always oversegment because if you have anything else than just spheres, the distance map will always produce local maxima, which produce a lot of unwanted segments of the same items. Well, that is all for today. I think the exercises today, they are less guided, but you can take a lot of code from this lecture notebook. So I hope you will come along with it. If there are problems and questions, don't hesitate. I'm usually looking on my mailbox, Slack. So just pop a question and I'll try to answer as soon as I can. Yeah, I think that was it for today. Well, I can keep the line open if someone wants to ask something. And then I wish you a nice day. It seems to be a very sunny, nice day, so enjoy that. Also, Tobias, enjoy your birthday. Hope you can celebrate it with at least someone, not being too isolated. And well, that was it for this week. Thank you.
Good morning.
Good morning.
I have a quick question. Good morning. I have a quick question. Thank you for the lecture regarding the skeletonization and how, so they created a way to kind of, or you created a way to figure out, okay, which road segments or how long road segments are, and like which road segments are which ones are junctions, and how would you go about by putting the image back together, so figuring out, okay, which is the main road, which are the joining roads.
Yes. So you want to recreate the structure based from the skeleton.
Yeah. Because I'm asking this specifically because this is something I've been trying to do in 3D. So I did for my semester project in 3D thing for the fracture fragment identification, trying to put these back together. And this is a bit of a problem since I use also the same like kind of principle of using an adjacency list. So figuring out which edges or which vertices connect to which edges. But putting them back together seems to be quite a challenging task.
Yeah. So you can't expect getting the perfect reconstruction.
Yeah.
I mean, you have reduced it pretty much. What you can do is, or what I would suggest is actually in-painting spheres. So if you combine the skeleton with the distance map, then you know on each skeleton point, then you know how big is the sphere that could be in-painted, and then you paint those spheres in, and then you would get probably a little bit blobby reconstruction, but you would get the shape more or less back of what the things look like.
Okay, so it's like a okay, I forgot my camera. So it's like using just taking a skeleton image and then just doing a 3D dilation along the skeleton.
Not really dilation, because each point along the skeleton is producing a different sphere. So it's more about painting in blobs or painting in spheres.
And then figuring out, okay, the biggest sphere is then so to speak, the main road. Yeah. And so what's that called specifically? Is that something you said last?
I think you have to look for terms like reconstructing skeleton or something like that.
Okay, great. I think about that.
Yes, and again, if you take a look at the literature about skeletonization algorithms, looking for Gunilla Boyer force and what was her name? Ingela something. Anyway, from the group in Uppsala, they did a couple of theses about 3D skeletonization in the late 90s, early 2000s. And there they also tried to actually reconstruct from the skeleton and see from which skeleton they produced the most natural reconstructions. I'm not so up to date with the latest literature.
So what I use the skeleton to basically find the labels, which I then use for the 3D watershed to separate the segments. And finding the correct labels is probably the most challenging part of it. So I think that would help definitely.
By the way, I see recording is still on. Do you mind if I put this one up? Do you mind if I put this on, or should I cut it away?
I don't really mind. So
okay. I just want to ask because that's about
privacy
protection, etc.
Yeah, no, I'm fine with that. Okay.
Yeah.
Great. Thank you. Thank you very much.
Good. Thank you. So I think that concludes today's lecture, and thank you all for listening.